So, yeah, my talk is on numerical experiment on the Hubble model. This is work that has been done over many years with many different collaborators. Among them are James LeBlanc, who's sitting somewhere back there, Henry Mullis, and Olivier Pacolet. The work is called Recordings of the Images. So, but before I start this, I would like to go all the way back to the beginning, the scientific method, right? Where we have theory and experiment, and the task of theory is it to predict nature, and the task of experiment is to validate those theories, falsify them, right? And then we have this feedback loop where we gradually increase our precision and refine our theories. And that works very well. I mean, we all know, for example, a experimentally motivated theory, Newton's classical models of mechanics, but then also experiments that have done based on theories that have been predicted. For example, Eddington's visit to South Africa to see closer eclipse. But if we go to our materials theory, then very often we know the theory is just a Coulomb or the 1/r interaction. Hamiltonian is up here, and in principle we could take this to predict the experiment, but in practice, of course, you all know that rather than predicting this, we run into problems, namely, we have just way too many degrees of freedom. So we need some approximate practical methods of applying quantum mechanics, right, which lead to an explanation of the main features of complex atomic systems without too much computation. And of course, the devil here is in the detail in these approximations. Right? What we typically do is we don't just take the theory as it's written down over here. We take the theory, we approximate the theory with some low energy effective model. We then approximately solve that approximate low energy effective model. And by the time we are back at the experiment, like if something doesn't work, we don't quite know what is it. Is it the approximate solution, the approximate model, or the approximate solution of the approximate model, right? And the reason for that really is we have very many particles, we have no small parameters, we have no perturbative methods, or perturbative methods fail, right? There are no controlled analytic approaches, and we are a little bit finessed. So that is the field where we, with sort of numerical methods for the mini electron problem, try to come in, where we're trying to say something about strongly correlated systems using modern computational method, and the only thing that we give up on the last couple of slides was this without too much computation, because we do most of these things on large computers and supercomputers. So with that, we can then take theory and experiment, have that all into play, but we hope to provide a computational box over here that gives us a feedback between theory and computation, between computation and experiment, and then have that scientific method restored at that feedback back. And I hope that over the next couple of minutes, I can give you 3 examples or 4 examples of how that works in practice. I'll start with a direct feedback to experiment, namely cold atomic gas experiments. I will then go to the pseudo gap as it is observed in NMR and show you some recent results of how we have computed an NMR signal. And then I'll say something about the feedback to theory, where we can test different types of theories and run them against calculations that are unbiased or differently biased. Now let me start with the first experiment, or the first numerical experiment here, the cold atoms problem. And this is a regime where computation believes that we can access a regime of parameter space, where also experiment believes that they can access the same regime of parameter space. So we have on one hand fermionic model systems that are accessible with state-of-the-art numerics and theory, and on the other hand, ultra-cold fermionic gases, right, that predict parameters or values for the same type of system. Here's the most simple system that you can come up with for electronic correlations that actually show collective behavior. That's the 3-dimensional Hubbard model. That Hamiltonian is somewhere over here. We've thrown out all of the quantum chemistry. All we have here is a kinetic term and a potential term, and we have electrons hopping here from side to side on a cubic lattice and interacting if that lattice is doubly occupied. that model is interesting because it's the model that shows collective behavior at the highest possible temperature. And because ultra-cold atomic gases are very cold in absolute units, but very hot in, fermion units or condensed matter units, that's probably the first place where one would see collective behavior. This is what this actually looks like in a lab. This is an ultra-cold atomic gas experiment. I have taken here a picture from Esslinger's lab in Zurich. Right? What you have is fermions suspended by laser beams in an atomic trap, counter-propagating laser beams, and the temperatures that you can reach in these things in the relevant units are far above the correlated anti-thermogenic phase transition at the moment. These systems are really nice because they're super clean, very stable, and they lack many of the complications that we have in typical condensed matter systems. For example, you don't have any dirt, you don't have any phonons, nothing like that. You don't have multiband effects of lattice vibration. From the theory side, what we do is we throw this system onto a computer. We have a many-body self-energy, that's a sigma of k and omega. You'll allow me to take that self-energy and expand it into a couple of basis functions. Here are my basis functions, independent basis functions. The frequency, the coefficients for those basis functions are then frequency dependent, and we can simply systematically concave this with a cutoff parameter nc. For nc going to 1, the only cutoff that makes sense is a completely flat basis function, that's the so-called single-side EMFP. For nc going to infinity, that thing will converge to the exact solution according to this expansion over here. And what we do then is we do a sequence of gradually increasing truncations here to get a result for the interacting main-body system. Here's a typical case of this. Our basis functions here are these little cubes in the Brillouin zone. We're going from systems that have something like 18, 36, 48, 56, 63, 84, 84, and 100 basis functions. And we use systems like that to compute for that three-dimensional powered model things like the energy, the density, the entropy, the free energy, the double occupancy, anything we care about. And we follow this up by a finite size extrapolation. Here you have the cluster size n. Here you have the quantity, in this case the energy. And you can see as we go to larger and larger system sizes, using a known finite size scaling here, we can extrapolate to the thermodynamic limit and get results that we believe have all the sources of errors contained for an interacting many-body system. Does that work? Well, we have claims from experiment for that model. We have claims from theory for that model. Here they are, both of them on the same plot. What you see in red are the experimental results. What you see in blue are the theoretical results or the computational results. All of this is without any adjustable parameter. And you can see as we come down in temperature, this is temperature up here, which corresponds to entropy in these systems. As we come down in temperature, there's a regime where the red and the blue dots are consistent with the error bars. The quantity that I'm plotting here, by the way, is a nearest neighbor spin correlation function. It doesn't really matter. But then at a temperature of about 1 or an entropy of about 1.5 or so, we can see that there are deviations between the blue curve, which goes up over here, and the red dots here, which are somewhere down over here. So there's a point where theory and experiment start to deviate. In this case, we actually understand what's going on. These are heating effects in the loading of the trap of the ultra-cold atomic gas system. That means that those values over here have additional errors which are not contained in that error bars, which are not estimated, and which are actually very hard to estimate in the cold atomic gas system. But anyway, what I would like to show you here is that there are correlated, strongly correlated, interacting fermionic systems where both theory and experiment, without any adjustable parameter, gives consistent results. This is for a hard model, and we have quite a few numerical methods that are all based on different types of approximations and different types of ways of looking at that problem, different types of formulations from stat mix to wave function to quantum chemistry. And we can in principle ask, well, what does one type of computation has to say about that model, and how does it agree with what some other type of computation has to say about that model? And we did that. We just simply reached out to the community, and we asked everybody who was interested in this to give us their best estimate of what a simple fermionic model system in 2 dimensions has to say. So this is now 2 dimensions, not 3 dimensions. And you see quite a few groups on here. My own group was doing dynamic cluster approximation. That was the technique that I just introduced. And dual fermions. We used diagrammatic Monte Carlo methods, density matrix renormalization, group theory, multi-reference projected Hartree-Fock. That's a method that comes out of quantum chemistry. UCCSD, that's unrestricted coupled clusters with singles and doubles and triples and quadruples. That's sort of the standard quantum chemistry way of looking at correlated systems. Auxiliary field quantum Monte Carlo, a numerically exact method at hand-filling, which has a constraint path that are as you go away from hand-filling. Density matrix embedding theory, variational Monte Carlo, all of these things, and all of these methods have approximations in them. Most of them are controlled, some of them are uncontrolled, but all of them have something to say about these model systems. And the question that we ask them is, how well do we actually understand those simple fermionic lattice models? Now, what you see over here is that the most simple quantity you can look at, the energy, and this here are different algorithms. And you can see that the typical energy that we're getting is down here at about 0.5% of an uncertainty at an interaction that is about as big as bandwidth and filling. We have different methods. Here, for example, MRPHF seems to completely fail for this. But you see DMRG, the most precise one-dimensional method, is not just the most precise one-dimensional method, it's also a very, very good method of looking at two-dimensional systems. Here, coming from small systems and gradually extrapolating to larger and larger systems, we get a result here, which is more or less consistent with the auxiliary field quantum Monte Carlo. Variational Monte Carlo methods also give a result. That result is slightly higher in energy than what one would get from DMRG and AFQMC because of a fixed node error. We have systems which struggle with metallic behavior. The coupled cluster methods are very good. They're really the standard methods for gap systems and for small molecules. As we increase the excitation level, that's the small parameter in these methods, and make them more and more precise, you can see how gradually you come closer to the result, but your method sort of gives up before you actually reach that result. But the takeaway message is that in this parameter regime, our maximum uncertainty in the correlation energy is about 0.5%. We could look at energies away from half-filling. This here is now as a function of temperature for a system which is still, and you can see here that there are initial methods on this plot. These are temperatures which come down from high temperature, and you could imagine that they sort of connect to the systems. Here, these are very difficult regimes of parameter space where Monte Carlo methods have what's called a sign problem and become exponentially expensive. Nevertheless, you can see that they actually are perfectly consistent coming from different ways of looking at these problems. Down here, we have the ground state methods. They're opened up over here. Again, you see AFQMC, DMRG, various types of density matrix embedding technique, variational Monte Carlo. And again, worst case here, we're typically about 0.5% off in the energy between the different methods. As we go to decoupling, these systems become much better under control. Now we have different types of finite temperature methods. This again here is temperature, this is the energy. And you can see that the blue method and the black method here perfectly agree with the error bars. These are different types of, well, one is a dynamical mean field type method, ECA. The other one is a diagrammatic Monte Carlo method, right? And as you take these methods and pull them towards the ground state, you can see that the finite temperature methods very nicely connect here to the ground state. And the ground state here in the decoupling regime is really very accurately captured by three methods that agree perfectly within the error bars. What can we say about correlated metals? Well, the correlated metal in this case, this is doped, fairly weak or intermediate coupling regime. The correlated metals are something that is really very well understood. Here you see various methods coming down in temperature and just smoothly connecting here to the ground state, which is perfectly captured by auxiliary quantum Monte Carlow, EMRG, and density matrix impedance. In here is the quantity that we usually care about in this community, the self-energy, right? It's the self-energy and Matsubara self-energy here plotted as a function of Matsubara frequency. And what you can see that is that in this small parameter that we're controlling in the pink method over here, we're getting something which is off. If we have, well, alpha of 3, as we increase alpha, we know that we're going to converge to the correct result. And indeed, as you go from 3 to 4 to 5 to 6 to 7 or so, by the time you're at 7, you're actually exactly on the reference curve that we have from a different method, which has entirely different amplitudes. So what that shows you is that for the Hubbard model, which is known as typically a very, very difficult model for numerics to solve, even in the worst case scenario, the uncertainties that we have with different methods in numerics, which have entirely different approximations and types of solving these systems, wave functions, density matrices, StatMech, diagrammatics, typically the uncertainties are less than 0.5%. In a large part of phase space, they're much, much less than 0.5%. And if you convert these things into Coop rate units and kelvins, the uncertainties that we're talking about in these systems are typically on the order of 10 kelvins. Right? That means that if you're looking for a D-wave superconducting transition at about 100 kelvins or so, those methods, all of those methods will have a resolution that is, good enough by about a factor of 10. So that's what I would like to do at the next exposition here. I would like to look at the Coop rates. And I would like to, again, go back to experiment and see what computation for these correlated systems actually has to say about the experiment. And for that, I would like to go to the pseudogap region of the Coop rates, which is a region in IPC materials where the electronic spectral function is strongly suppressed along the Brillouin zone face, but not along the zone diagonal. You see that Brillouin zone over here, and this here is the Brillouin zone face, this here is the zone diagonal, and as we go here from pi 0, that part over here towards pi n pi half, that part right here in the middle, you can see that the spectral function is originally suppressed. It has this dip over here, right? And then as we gradually go towards pi n pi half, you see this enhancement of the density states. So there's a key physics dependence on momentum around the Fermi surface, the difference of spectral function around the Fermi surface, and a doping dependence of the region that can support quasi-particles. And you can see that down here in Orte's plot that I lifted from Chen et al., right? As we are very close to half filling, there is a fairly small region that can support metallic behavior. As we go away towards optimal doping, that region gradually grows here, right, and takes sort of the shape of the non-interacting Fermi surface that we have over here. So all of this is weird. If you go and look for that phase in the phase diagram, here is the phase diagram of the Coop rates. Here are hole dope, these are the electron dope materials. So the pseudogap is a region of phase space that appears on the hole dope side here for dopings that are smaller than optimal doping, and for temperatures that go up to pretty much about 300 Kelvin. And no matter what the experimental probe you throw at this, and up here I have all this from ARPES to STM to various types of other experiments, right? You're going to find a signature in those experiments of the pseudogap, right? This here is a collection of plots of many of these things. Now, originally, the pseudogap was actually discovered, or one of the very early plots here is this one by Takigawa and collaborators, which shows the NMR night shift as a function of temperature. What you would expect at a phase transition like the superconducting transition is that above that transition, the night shift simply behaves like a metal, and then you enter the superconducting state, and it just plummets and goes back to zero. What actually happens is something that, up here you can see that the actual NMR night shift that you're getting is strongly suppressed from what you would be expecting, and then at the superconducting transition, there's not that much happening. And that has led people to speculate that really what's happening here at the superconducting, above the superconducting transition, is what's happening below the superconducting transition. We already have pretty much the physics is established there, right? We just have to somehow push that PC up a little bit, and then we could have a PC that is much higher. And I'll have something more to say about that type of argument in just a bit. But just to scare you, right, we can look at these NMR quantities with theory. Here are susceptibilities, which are given by Green's functions, and these Green's functions are numerically accessible in Monte Carlo methods. With a little bit of massaging of these Green's functions, Fourier transforms, summations with the right symmetry factors, and so on, we can get information about the superconducting pairing. We can get information about the magnetic signal. I think James will later say more about that. And we can directly extract the night shift, the relaxation time, and the spin echo decoy time of these materials. You can see all of these are functions of various types of magnetic susceptibilities that we have over here. So that gives you the program. We'll just simply compute the magnetic susceptibility, extract the night shift, the relaxation time, and the decay time, and look at it. Now in experiment, what you see here is the night shift as a function of temperature, and plotted here for different doping curves. You can see that in the underdose, the night shift shows this very clear suppression, goes down here. In the overdose, that night shift goes up towards large values. Here is what we're finding in simulation. In the underdose regime, we find our curve here goes up and then turns down as soon as we go past the pseudogap. Now the pseudogap, as determined in ARPES, or as determined in the single particle properties in that same calculation, is indicated by these arrows here. So you can see that the overturning here, the downturn of these values coincides with the single particle pseudogap that we're finding. And then as we keep doping these things and making them more and more metallic, our curve here, our night shift, our simulated night shift goes up, and that pseudogap signal disappears from our simulation. Now, the interesting thing here is that for calculations like these, we've thrown out all of the crystal structure. All that we're left with is a hopping parameter, a T prime, and an on-site interaction. And in addition to that, we are honest about the correlation structure of our many-body system. Right? So what gives you these pseudogap type behavior is not some sort of multi-orbitally effect, but just a many-body correlation effect that we have in the absence of long-range order. Now, out of this, we can look at the energy scale of the pseudogap. Right? These are experimental data on the compounds here, where you can do an Arrhenius plot and extract the energy scales. And you can see that if we do exactly the same here, and extract our energy scale, and then take that data and we compare it to the pseudogap as computed from the single particle spectrum up to a scaling factor, which is, by the way, the same in experiment, we find that the two pseudogaps here track each other perfectly. So they really seem to be describing the same type of physics on the two-particle level for the NMR and on the single-particle level for the ARPES. Now, if you look at the spin echo decay times, then essentially before the superconducting transition, you'd find no signal whatsoever. And so these downturns that you see over here, these are input superconducting. And indeed, if we looked at that here, you should compare that plot to that plot. You find again the same doping behavior as we add more and more particles and the same temperature. So that seems to work too. And finally, the P1, the NMR relaxation rate, shows also interesting behavior on the single layer compounds. It just simply keeps going up until we hit the TC, and then it plummets. Now this is NMR data on the copper sites. If you look at the NMR data on the oxygen sites, you actually find something that is very reminiscent of the night shift. And indeed, when we go and we simulate this, now we don't have copper and oxygen. We just have different symmetry factors that belong to these lattice, but we simulate this here for the copper sites, for the copper symmetry factors, and for the oxygen sites, we find indeed that very different signal with this one here reminiscent of the night shift, and with that one over here reminiscent of the experimental data that we find over here for that. So that here was interpreted as having two different types of electrons originally. Right? One of them undergoes the pseudogap physics, the other one is completely immune to it. And you can see that in a calculation like this, we don't have different electrons, we just have a single band that is doing these things, and very clearly, it is just a symmetry factor. So now very briefly, I would like to go to the last thing and interact a little bit with theory. We could just go and look at the superconducting phase diagram, compute it. This is the phase diagram that we're finding. And as we come up from weak coupling here, go to larger and larger doping, and to cuts along here, right, we find an order parameter that is coming up, gets maximal, goes down again, and then builds a very nice dome here of the superconducting order parameter at temperatures, at the interaction strengths that are large enough to be on the order of about the bandwidth, where we have a mod insulator at time filling, an intermediate pseudogap, a superconducting region, and then a perfect Fermi liquid. Now, theories of superconductivity usually predict a mechanism for causing that superconductivity, and usually you go superconducting either because you can lower the potential energy or because you can lower the kinetic energy. Right? If you believe in weak coupling type superconductivity, then you're going superconducting because you can lower the potential energy, so-called potential energy driven superconductivity. On the other hand, if you believe in RBB type superconductivity, then your wave function gets scrambled over here, and you go superconducting and lower in that term the kinetic energy. Now, what we find is that neither one of those pictures covers all of phase space. In the overdope, you go superconducting because you can lower your potential energy. In the underdope, you go superconducting because you can lower your kinetic energy. Somewhere in between, there's a crossover. That crossover is the onset of the normal state pseudogap. So it has to do with a change in the normal state, not that you're comparing to, not in creating the superconducting state. Back to these pictures of, well, the idea of preformed pairs above the DC. We can now, because this is theory, just go to our superconducting compound and apply a superconducting field to it and see how the compound reacts to it. And if we do that in a weak coupling regime, we get a fairly large susceptibility to an applying magnetic field, meaning that that thing really wants to go superconducting, and it's almost there yet. As we then enter the pseudogap regime and finally go into the normal state regime above the superconducting position, where we have a pseudogap, and we apply a D-wave superconducting field to that pseudogap state. You can see that the response to that applied superconducting field is very, very small. And that gives you an indication that the state that we're finding above DC, that pseudogap state in the underdope, is really not a precursor of a superconducting state. It's something that is completely different. Now, even though our NMR signal shows that suppression that has led people to believe that what you're finding is preformed pairs and essentially already an established superconductor, that is not actually what is happening within our simulation and our approximations. All right. And I think I'm actually out of time, right? All right, so let me leave it at that. And come to the conclusion. I hope I could show you that we actually have these systems fairly well under control. If you don't like comparing to other numerics, at least you'll allow me to compare to other experiments where we have unbiased experimental data that claims that they fully understood the model, and unbiased numerical data that claims that we fully understood the model, and those actually match up perfectly until one of them breaks down and we know why it breaks down. I hope I could show you that if we take simple theories of superconductivity, they may be correct in some part of it, but so far we have not found a theory of superconductivity that is correct in all of the regime of phase space. And then I skipped this here, but we'll maybe hear more about this. Thanks.
Question?
Professor, there are many simplified model, Hubble model. I'm I'm interested, curious whether you find some special results that you can only find in Harvard model, but with all the simplified model, you don't find such results. There is some unique results of the Harvard model.
So I don't quite know how to answer this, right? The way we usually proceed is we strip out as many parameters as we can, and then we see if in that minimal model we can find physics that is found in, let's say, experiment or so. Right? I mean, NMR is a good example for this. Once we're at the Hubbard model, there's really nothing more to take out without destroying the fermions. Right? So once we're at that level, we can test, what is still in there and what requires other type of physics. Turns out that for things like the NMR that I've shown you, for things like the pseudogap, it's enough to just be honest about your correlations, or do the correlations non-perturbatively, but otherwise you can have local interactions, single bands, things like that. Now, whatever is not contained in this must come from other type of physics that we've thrown out, right? Multiband effects, quantum chemistry, anything like that. Of course, if you try to, let's say, you try to simulate the Rix experiment or something like that, there you have to know about your highly excited bands that we've thrown out here. But as long as you're looking at a probe that essentially measures the energy scale for which that model has been fitted, which is anything below about an eVolt or so, you should be fine using this.
Now, the term Cooper pair comes up in funny contexts with Cooper excited. You have very small Cooper pairs. You shouldn't think about them in terms of Cooper pairs. You have what would you say about Cooper pairs within this model in terms of sort of what they look like either in field space or?
Oh, so well, what I like to think about are anomalous order triangles or anomalous green function. A non-zero expectation value of CC or C dagger C dagger. Right? That is superconductivity. Here we allow for any sort of superconductivity, and then we test for the symmetry. Right? And the symmetry we find here is D-wave. That's not really surprising. I don't really like pictures where you have one electron going that way and the other electron going that way, right? Because these are many-body systems, and you shouldn't think of them in terms of single things going somewhere.
Right, but an effective two-particle basis to superconductivity. It's never mind. It's something I'm very curious about, but it doesn't seem like it's.
Yeah, I'm a bit puzzled about you trying to compare your methods with other methods in terms of total energy, and you saying, oh, everybody is actually as accurate as within 5% of the total energy, right?
About 0.5%.
0.5%, yeah.
For the
So
energy.
that means two things, right? One is that, well, everybody does it well, and it means that maybe the test in terms of total energy is not so valuable, right?
Oh, that's right.
Yeah, that's maybe one thing you can
Yes.
say. The other thing you can say as well, maybe you want to compare total energies, then you have to be really compared, because that 0.5% effect matters a lot. I mean, if you look at density functional theory, right, you cover huge total energies, but to get it right, you have to be extremely accurate, and they do, right? So, but of course, the test would be much better if you look at excitation spectra and all that, because then all these different models take a completely different spectra.
Right. So that of course you're right. Right. And I have a couple of answers to that. One of them is we're actually doing these tests at the moment. Another answer for that is that the energy is a single number, and there's a very large parameter space. So in order to make a meaningful comparison, you have to find between as many different methods as you can find. You have to find a single number that everybody can compute, and the energy is such a number. You will not get excitation spectra out of the quantum chemistry method because they just haven't been designed to do that, right? You will not get decent stat-mech ensembles out of a wave function method and decent wave functions out of a stat-mech method, right? Yeah. So if you're looking to, see what those methods all can say, it's the energy that is robust for this. But you're totally right. I mean, the excitations are, that's a lovely question. We'll have something to say about that.
So what you say is that's what you do well. You gear up to do.
Oh yeah.
To do just that also.
Well, that's right. But finding out where it works at all and how it works and where it breaks down and why it breaks down.
So I think everyone